This set of videos covers the quantum mechanical model of the atom. It is, at this point in time, what we think the electron cloud looks like and what it does and how it behaves. And I say think because you never know. We could learn something new and have to modify this idea in order to fit with the new evidence that we have. So quantum mechanical model, also known as all those different things you see there, quantum wave model, wave mechanical model, quantum model, so on and so forth. You see the word wave in there, you see the word quantum in there, you see the word mechanical in there. So any of those versions you will hear it referenced to, depending upon what source you go to. So what I want to start out with is a video that just refreshes your memory on what the Bohr model is about. So take a listen to this one and then we'll move on from there.
When an atom absorbs energy, it could be electrical energy, thermal energy, or electromagnetic radiation, it tends to re-emit that energy as a photon. This is the principle behind neon signs. If you pass electricity through a gas, the gaseous atoms give off light. Different atoms emit different wavelengths of light. For example, if you pass the light from a hydrogen lamp through a slit and a prism, the light will be divided into its component wavelengths. The result is called an atomic spectrum. Hydrogen spectrum is composed of 4 distinct wavelengths in the visible spectrum. If you perform this experiment with helium, however, you would get a different spectrum with 6 distinct wavelengths in the visible spectrum. Each atom has its own unique spectrum. If you perform this experiment with white light, you would see a continuous spectrum. The Bohr model was developed to explain these results. In the Bohr model, the energy of an electron is quantized, which means an electron in an atom can have only particular discrete values of energy. We label these values of energy as energy levels. N equals 1, N equals 2, N equals 3, and so forth. Typically, an electron is in its ground state, which means the lowest energy level that is available. But when an electron absorbs energy, it's said to be excited, and it jumps to a higher energy level. This higher energy level is less stable, because we've separated opposite charges. The nucleus is positive, and the electron is negative, so energy is required to separate them. The electron will spontaneously drop back down to a lower energy level, as it is attracted to the positive nucleus. When it drops from a higher to a lower energy level, it emits a photon with an energy equal to the difference in energy between the 2 energy levels. Each of the distinct wavelengths present in the atomic spectrum for an atom correspond to transitions between 2 energy levels in the atom. In hydrogen, for example, when an electron drops from the N equals 3 to the N equals 2 energy level, it emits a photon with a wavelength of 657 nanometers, which corresponds to red light. Since each element has a unique atomic spectrum, we can use a flame to excite electrons in a metal and observe the color of light that is emitted in order to identify the metal. This is called a flame test for a metal. The creators of fireworks apply the concept of atomic spectra when they use shavings of different metals to achieve different colored lights. When an atom absorbs...
Sorry about that. Okay, so there was a review of the Bohr model. So let's talk about what was right and what was wrong with what Bohr said. So we know that Bohr had it right in terms of energy levels being quantized. Electrons are associated with particular levels. They can jump to higher levels. They can fall to lower levels. but you can't go in between. So it's kind of like you saw this analogy before. It's kind of like a ladder. In order to go up a ladder, you have to put your foot on a rung. If you put your foot between rungs, you're going to get nowhere. Your foot's just going to come back down to that rung that it was on originally. So that's what we mean by quantized. You can only put your foot in certain places. The electron can only absorb certain amounts of energy. We also know that electrons can absorb energy and move to an excited state, release energy, move back down to their ground state. So essentially, we know that the idea of emission spectrum are right. So here's kind of a really cool visual of what the visible emission spectrum for all the different elements on the periodic table looks like. All right, unfortunately, he got some things wrong as well. So he got wrong the fact that electrons don't really travel in defined paths, like planets orbiting the sun. He also got wrong that this applies to any other atom except hydrogen. So Bohr's model only works for hydrogen. Well, actually, it works for any species that has one electron in it, like He plus or Li2 plus. But once you put a second electron in there, Bohr's ideas don't work anymore. So he had part of the story, he just didn't have the whole story. So the quantum model really comes about by two gentlemen, Schrödinger and de Broglie, who spent, along with a lot of other scientists, spent some time looking at Bohr's ideas and other information that they got from various instrumentation and measuring and so forth. And they came up with what we now call the quantum mechanical model. But again, remember, it has many different names. So let's take a look at the quantum model in a little bit more detail. Okay, the orbits that Bohr refers to are simply the first layer of organization of the electron cloud. Bohr was not totally wrong with his idea. He just didn't have the whole story, like I said before. So the quantum model breaks the space around the electron cloud into 3 levels of organization. So we're going to take a look at these 3 levels. So principal energy levels are what you're used to seeing as Bohr's orbits, Bohr's rings, n equals 1, 2, 3, 4, and so forth. So principal energy levels are Bohr's orbits. They are the largest divisions of space, and really what they are is they represent a radius, a distance from the nucleus, all the way around the 3-dimensional part of the atom. And as you go from the closer rings to the further away rings, just like Bohr said, energy is going to increase. So you've got these different rings, and energy increases as you go out. But what Bohr didn't understand is that it's more, electrons don't just stay in this area. It's much more complicated. The organization of each of these rings, so to speak, is much more complicated. So here's the rest of the ideas. So in the principal energy levels can be broken down into what we call sublevels, and we give them letters, S, P, D, F, and so forth. So the sublevels each have their own specific size, shape, and energy. So we'll get into all of that stuff. But you can see there's, in the different principal energy levels, there's some only have an S, some have SPDs and Fs, and so forth. The shapes of the sublevels represent the locations of electrons based upon some really complicated math based on wave properties and motion, and that's stuff that we're really not going to learn how they got it. We're just going to accept the fact that they got it. So these sublevels are then further broken down into orbitals, and sometimes they're just labeled in terms of, in the 3-dimensional space, where are they? So for example, X, Y, and Z axes. So like I said, orbitals are the smallest division of space. They really represent the orientation of the electron motion. So where in that 3D space is the electron moving? So for example, a p sublevel has 3 orbitals. They are oriented along the x, the y, and the z axis. So you can see them represented in that picture there. Orbitals are really like, oops, what happened? A probability map. They show you where an atom can be found 90% of the time. Okay, so orbitals are really probability maps. They're showing you where the electrons are likely to be. Most of the time, not all the time, but most of the time. Orbitals don't have actual walls. They are just areas in three-dimensional space where an electron tends to hang out. You cannot predict within that orbital, you cannot predict their electron's location, you cannot predict how fast they're going, especially simultaneously. But you can predict, like I said, where you're likely to find them. So here's a really good analogy. So think about the summertime. When it's dark in your backyard, if there's no outdoor lights on anywhere, you can see fireflies flashing, and they light up and then they stop lighting, and then you don't know where they go. If you're standing far away and you can't actually see the insect, you don't know where the light's going to be next. But what if in the middle of the yard, I hung from a tree in the middle of your yard some firefly pheromones? Those are basically sex hormones that would attract the fireflies to it. If I hung that pheromone in the middle of the yard, what would start to happen? The fireflies would all start to move towards that pheromone because they couldn't resist. So now as their little lights light up, you start to see a concentration of all the fireflies around that center tree where the pheromone is. As they continue to move around there, they flash, they stop flashing, but basically the amount of light, the amount of flashes you would have around that pheromone is going to be much higher than you would have in the rest of the yard. Now, does that mean the fireflies can't go away from the pheromone? Absolutely not. A firefly can wander off and flash at the other end of the yard. But for the most part, because of their desire to be attracted to that pheromone, they're going to stay nearby. And that's really what an orbital is. It's simply showing you an area in space where you're likely to find an electron around the atom. So I want to go to this analogy because sometimes it's helpful to think about it. So think of the atom electron cloud as being like an apartment building. Principal energy levels represent the floors. So you have the first floor, the second floor, the third floor, so forth. Sublevels represent the apartments. So on any floor, you could have multiple apartments. Plus, those apartments could be different sizes. You could have an efficiency. You could have a 1-bedroom, a 2-bedroom, a penthouse, and so forth. So you've got different sized apartments. Well, within those apartments, because they're different sizes, you have a different number of rooms. Think of the orbitals as being the rooms. So in a small apartment, you only have a couple rooms. In a big apartment, you have a lot of rooms. Same thing as sublevels. Smaller sublevels, fewer orbitals. A bigger sublevel, more orbitals. And then the electrons represent the people living in those apartments. The electrons stay in the orbitals, basically in that area. And so the more orbitals you have, the more people you can have in the rooms and the sublevels and the principal energy levels. So it's just kind of a nice visual to think of it that way. We're going to go on and take a look at the different kinds of sublevels and their shapes and so forth, but I'm going to wait to do that for the next video installment.